Hello. So in this video we will talk about an application of trees, namely prefix codes and Huffman coding. So just a recap, a tree is a special kind of graph which is connected and has no cycle or circuit. Okay, and a connected graph is a tree if and only if every edge of G is an articulation point of. So these of G. So these two are alternate definitions of trees. And a graph with no simple cycle that is not connected is a forest. So these are the definitions which we are going to use in our application here. So what are prefix codes, for example? So now prefix code, any code is, so when we say code, it's a representation. Okay, so it's some representation of any symbol, any text, any talk in some different kind of representation which is efficient in some way. Okay, so what kind of efficiency comes to mind when we are talking about strings in a, for example, in when we write some text in our emails, for example. So the efficiency which comes to mind is that if I have a very long text, how can I represent it in the most efficient way in terms of saving space, right? So if we want to save space, in other words, we want to do compression here. Okay, so when we say encode data, then it can mean, it not always means, but it's very logical to assume that it can mean compressing the data such that the information is not lost. Okay, but when we compress the data, not that we want to prevent, not only that we want to preserve the information, we also want most efficient representation. Most efficient means that it has to be have minimum possible length out of all the possible of options. Okay, of all the possible options. Okay, so the strategy is something like this. So now remember that if we want to find the average, if we have like say 10 symbols, 10 symbols with some probabilities. Okay, so the average is, this is summation x times px of x. Okay, so this is a little bit of probability here. So what we want to say is that um, if we have some symbols and x can take any of the value of any of those symbols, so then what we want to do is we want to multiply x by the probability and take the sum from x is equal to all the values it can take. Okay, so that is my average. Okay, now if in this summation, if I assign longer strings, so if x is my length, so if I assign longer strings to lesser probabilities and shorter strings to more probabilities, then one can appreciate that this sum will be minimized. So that is why the idea is to assign a shorter code than those with the lower probability. So higher probability of appearance would be assigned a shorter code than those with a lower probability, and hence this average is minimized. Okay, and why do we call them prefix free codes or prefix codes? Because the code of one symbol cannot be the prefix of the code of any other symbol, and this is to avoid ambiguity in decoding. So for example, if I say my symbol, for example, a is 0 1 and my symbol b is 0 1 1 and my symbol c is just 1, and then I want to send 0 1 1. I send 0 1 1. So at the receiver, he does not know whether this is A, C, or it is B. So this happens because one of the symbols, B 0 1 1, has a prefix of another symbol, which is 0 1. So that is why this ambiguity arises. So in order to avoid that, we want to uh, ensure that this prefix free condition is maintained. So prefix codes, that's why we call them prefix codes. Okay, so the strategy is this. Remember that if we have a tree, what so, and this is my tree, for example, and these are my leaves, for example, then this and this are called ancestors. Okay, so the strategy is that if the leaves represent a symbol, then any of its ancestors cannot represent any other symbol. Okay, so we'll see what it means in detail when we start doing our example here. So this is a Huffman coding example is exactly based on this kind of strategy, this strategy and this strategy, that higher probabilities for correspond to lower length, and if all symbols are represented by leaves, and no internal vertex is represented by a symbol. Okay, so this is like just a pseudo code, so I'll just go through them quickly and then we go to the example here. So input set of symbols AI with probabilities or weights PI. Okay, if and then a starting point, our F is a forest with n rooted trees, which means it's not connected. Those n rooted trees are not connected, and each tree TI has label AI and weight PI. So we keep on moving unless we make F a tree, and we replace the rooted trees Ti and Tj. So we choose Ti and Tj such that they have the least weights from F, and by convention Pi is greater than or equal to Pj, and we make a new tree such that Ti becomes the left subtree and Tj becomes the right subtree, and the edge to Ti is labeled as 0 and edge to Tj is labeled as 1. Okay, and the new tree is assigned a weight of the summation of Pi and Pj. And then once we have F as a tree, then the code of symbol AI is the concatenation of all the edge labels from root to vertex AI. Okay, so we start counting from the root to that vertex and see what combination of zeros and ones we get. Okay, so this can be extended to m-ary case, but we will come back to that once we do the example for binary case of Huffman coding. Now we have these symbols and these weights. So my first point is I will just make n rooted trees which will be not connected. Okay, so this is my A B08. So my first step is to combine F and C. So C and F. So then my A remains like this, my B remains like this, my C and F, they are now like this, and my D remains like this, my E remains like this, my G remains like this. So this is my F because F has a higher weight than C, and this is my C, and this is my A, this is my B, this is my D, this is my E, this is my F, not F, G. Okay, so these weights I'm not going to repeat them because they are the same, but F and C, I'll just add F and C, so this becomes 0.12. Correct. Then what are the two minimum now? Now the two minimum are A and G out of these ones. So I will combine A and G. So this becomes, so out of A and G, A has a higher weight, so A and G. And if I sum the weight of A and G, I get 0.18. And then B is the same. Then I have F and C, same thing. And I have D and I have E. Okay. So just for sake of, because now we are far from our starting point, so and this is my E, so D is 0.15 and E is 0.3. So out of these two I will choose this FC and D. So this becomes, this is just this is just B. Then what is the, D has a higher weight than FC, so this becomes left and this becomes right. Okay, and then this is my E. So this is my A, G, this is my B, this is my E, and then if these two are combined, this is 0.2. Okay, then if I combine, what should I combine now? Now I should combine A, G and B because these two have the lowest weight. Okay, so this is 0.3, this is 0.25, this is 0.18. So then this becomes, this is my A, this is my, sorry, this is my B, this is my A, this is my G. Okay, and this is 0.43 here, and this is just repetition here, and so this is D, this is my F, and this is my C, D, F and C. Okay, and this is my E. So this is 0.27. This is my E, which is 0.3. Okay, so then this guy, I will just combine this and this. So this becomes E on the left, and then so E, D, F, and C. So 0.57, and then I'll combine this and this. So this has the higher weight. So I'll just say this is my left subtree, and this is my right subtree. Okay, so this is my E, this is my D, this is my F, this is my C, this is my B, this is my A, and this is my G. So now I'll start labeling 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, and 1. Okay, so then based on this tree, what are my codes? A, I have 1, 1, 1, 0. So I'll say 1, 1, 0. Okay, so similarly for B, I have 1, 0. For C, I have 0, 1, 1, 1. For D, I have 0, 1, 0. For E, I have 0, 0. For F, I have 0, 1, 1, 0. And for G, I have 1, 1, 1. Okay, now note that B has higher weight, so it has a shorter code. Similarly, E has a higher weight, so it has a shorter code. Okay, so this is how we do the Huffman coding for a set of symbols. We start with the forest and we end up adding the rooted subtrees of minimum weights until we get one connected tree. Okay, one tree actually. Tree is already connected. Okay, so this is about Huffman coding in the binary case. Now let's see how can we do for the m-ary case. So there are only two differences. So in the first step, we choose this amount of trees to combine, and in all next steps we choose this amount of trees to combine, and they are also based on their weights. Okay, so now let's say this example here in which we have to encode these symbols based on these weights. So again we'll start with just writing them out: A, E, N, R, T, and Z. So this is 0.25, 0.3, 0.1, 0.05, 0.12, 0.18. Okay, and then what is this guy? This is 1 plus how many symbols do I have? I have 6 symbols. So 5 mod 2, which is equal to what? 5 mod 2 is 1, so 1 plus 1 is 2. So I will choose 2 symbols in the start. Okay, so I'll just choose N and R. Okay, and N and R, N has this higher weight, so I'll say A, E, and then N and R like this, and then T and Z. So A, E, N, R, and T and Z. And then I'll say the weight of this is this plus this, so 0.15. Then how many? M is 3, right? Now I have to choose 3 of them. So I will choose 0.15, 0.12, and 0.18. Okay, so the highest of them is Z. So I'll say Z here. Then I have 0.15, and then I have T. Okay, so Z here, N and R here, and T here. So this is labeled as 0, 1, then this is labeled as 0, 1, and 2. Okay, and then A, E, R right here. Okay, and the weight of this guy is this plus this plus this, which is 0.45. Okay, and then this is just 0.25 and this is 0.3. So my final is 0.45 will come here, then 0.3 will come here, and 0.25 will come here. So this is my A, this is my E, and this is just, I have to just copy this whole story. So this is like this. So this is Z, this is N, this is R, this is T. So 0, 1, 2, 0, 1, 2, and 0, 1. Okay. So my A is what? A is just 2. My E is what? E is just 1. My Z is what? 0, 0. My N is what? 0, 1, 0. 0, 1, 1. And my T is what? 0, 2. So this is the code in terms of my m-ary Huffman coding. So the only difference is that in the first step we have to choose these many symbols, and then we have to choose just m symbols at a time based on their own weights. Okay, so this is a small example of Huffman coding based on binary, in the binary case and in the let's say 3-ary case. And I hope it was easy to understand, and thanks for watching. Hope you liked the video.